Physics Made Easy Kota. Welcome on our YouTube channel. My name is Daljit Kaur, and in this video lecture we are going to understand about the concepts of the chapter electromagnetic induction. In this video lecture we are going to learn about the self-inductance and mutual inductance. So the first topic is a self-induction. Self-induction is a property of the coil that we are using in this given diagram. So according to this is the property. Due to the result, it opposes the growth or decay of the current flowing through this coil. You can see that in this figure we have a coil that is connected to a battery through a key. When the key is pressed, the current in the coil start increases. Due to increasing current in the coil, the magnetic field and hence magnetic flux linked with the coil also increases. As a result of this, induced EMF is set up in the coil, and according to the Lenz law, the direction of induced EMF is such that it opposes the growth of current in the coil, and this delay the current to acquire the maximum value in the coil. So when the key is released, the current in the coil start decreasing. So the magnetic flux linked with the coil decreases, and as a result of this change in magnetic flux, induced EMF is set up in the coil itself. Then again, according to the Lenz law, the direction of induced EMF is such that it opposes the decay of current in the coil, and this delay the current to acquire minimum or zero value in the coil. This property of the coil, which opposes the growth or decay of the current, is called self-induction. Self-induction is also known as the inertia of electricity, as it opposes the growth or decay of the current in the circuit. Magnetic field at any point due to current carrying coil is directly proportional to the current. Therefore, the magnetic flux through the area bounded by the current carrying coil is directly proportional to the current flowing in the coil. So, here is a relation, that is the flux directly proportional to the current, and this L is known as a constant of the proportionality, which is called as a coefficient of the self-induction. If I is equal to 1, then we have the expression L is equal to the magnetic flux. So here is a definition. Coefficient of self-induction is defined as the magnetic flux linked with the coil when unit current flows through it. Then we can use the Faraday law to establish the relation between the coefficient of the self-induction and the EMF. So according to the Faraday law of electromagnetic induction, epsilon, that is the induced EMF, is equal to minus of d phi b divided by dt. We know that the flux is equal to Li, so just replace its value. Then we have epsilon is equal to minus L di over dt. If minus di over dt is equal to 1, that is the rate of decrease of current is unity, then we have the expression epsilon is equal to L, and so we get the definition or the relation of the coefficient of the self-induction with induced EMF. Now we are going to learn about the relation of the self-inductance for the group of the coil. So in this case, the two cases are possible. The number one, when the coils are connected in series, and the number two, when the coils are connected in parallel. So from the diagram you can clearly see that there are the two coils of inductance L1 and L2, and let us suppose epsilon 1 and epsilon 2 be the potential difference across these coils, and for the series connection the total potential difference is equal to epsilon, that is equal to epsilon 1 plus epsilon 2, and since the rate of change of current in both the coil is the same, so we can write the equation of the total potential difference in terms of the inductance. So by using the formula we write epsilon we can now write it as minus L di over dt, and for the epsilon 1 minus L1 di over dt, and for for the epsilon 2 minus L2 di over dt. After doing the calculation, we have the relation L is equal to L1 plus L2. So that is the total inductance increases in case of the cells connected in series. Now the case when the cells are connected in parallel. So for the parallel combination, now the total current is I is equal to I1 plus I2. Just differentiate this value of the current with respect to time t. Then we have the expression di over dt is equal to di1 divided by dt plus di2 over dt. Now we know the expression that the epsilon is equal to minus L di over dt. So just to rearrange the terms, we have the value of di over dt in terms of the L, that is in terms of the coefficient of self-inductance. Then replace the values in the equation where we have di over dt or di1 dt and di2 over dt. Then we have the final expression in term of the coefficient of the self-inductance. So for the parallel combination, L is equal to L1 L2 divided by L1 plus L2. After self-induction, the next topic is a mutual induction. So in a given figure, you can see we have a coil which is connected to a battery through the key. This coil is called as a primary coil and given the name with the help of the alphabet capital P. Another coil placed near the primary coil and which is connected to the galvanometer is called secondary coil. When key is pressed, galvanometer shows a deflection. And what is the cause for this? Actually, the cause is a mutual induction. So that is when the key pressed, current through the coil P began to increases because this is connected to the battery. As a result of this, magnetic field around the coil P also increases. So magnetic flux linked with the secondary coil also changes. The induced EMF is produced in the secondary coil due to change in the magnetic flux linked with the coil. Hence, the current flow through the secondary coil, which is indicated by the deflection in the galvanometer. And this phenomena is known as a mutual induction. So that is a producing or inducing EMF in a secondary coil due to changing current in the primary coil. Magnetic flux linked with the secondary coil is directly proportional to the current which is flowing through the primary coil. So after this equation, that is the phi s directly proportional to IP, by removing the sign of the proportionality, we have the constant which is known as the coefficient of mutual induction or simply mutual inductance. We can define it in the terms of the flux by putting the current IP is equal to 1. Then the mutual induction of two coils is defined as the magnetic flux linked with the secondary coil due to flow of unit current in the primary coil. In this question, we have to calculate the magnitude of induced EMF in a coil of inductance 1 millihenry in which current is changing from 0.1 ampere to 2.1 ampere in 0.01 second. So we have the given data. First of all, we have the value of the inductance. We can convert it into Henry as milli is equal to 10 raised to power minus 3. So it changes to the 10 raised to power minus 3 Henry. And in the question, it is mentioned that the current is changing from 0.1 ampere to 2.1 ampere. So we have the value of the DI 2.1 minus 0.1 final minus initial, and the time is also given in which it is changing, that is the dt. So by using the formula epsilon is equal to L di over dt, we have the final answer, that is 0.2 volt. Next question. For this question, we have to calculate the mutual inductance between two coils when a current of 2 ampere changes to 6 ampere in 2 seconds and induces an EMF of 20 microvolt in the secondary coil. We already know about the formula of the EMF in terms of the mutual inductance, that is epsilon is equal to m dip divided by dt. So just rearrange this formula. We have the value of the induced EMF 20 microvolt, convert it into volt, as micro is 10 raised to power minus 3. We have the formula of the dip over dt, that is the 6 and 2, that is, it is also mentioned, it changes from the 2 ampere to 6 ampere. So we get it by 6 minus 2 divided by the time in which it is changes, that is the 2. So by doing the calculation, we have the answer 2 ampere per second. So just put all the values in the given formula of the mutual inductance, and we have the final answer 10 into 10 raised to power minus 3 Henry, which can be also represent as 10 microhenry. So now in the next question, a pair of adjacent coils has a mutual inductance of 1.5 Henry. If the current in the one coil changes from 0 to 20 ampere in 0.5 second, what is the change of flux, the linkage with the other coil? So for this we have the value of the self inductance, and also it is given the current changes from 0 to 20. So we apply the formula final minus initial value, 20 minus 0. So the answer is 20 ampere, and this is change in a given time, that is a 0.5 second, which is the dt. So we apply the formula epsilon is equal to m di over dt, and we have the value of the epsilon, that is a 64. But for this case we have to calculate the what is the change of flux linked with the other coil. We already know the formula of the induced EMF in terms of the flux is epsilon is equal to d phi b divided by dt. So just rearrange this formula. We have the d phi is equal to epsilon into dt. Put the value of the epsilon 60, get it multiplied with the dt, that is a 0.5, and we have the final answer. So this is for the practice. Calculate the inductance of the three inductors connected as shown in the figure.